Well, hi again, this is Bob, and we're getting ready to begin the last chapter of our course, and it's Chapter 8 deals with hypotheses testing, and we're going to first look at what they call the traditional method, and then other methods that they have, the book has provided for us. But the first thing I wanted to say is this is a really important section to make sure that you've read through. And I'm going to try to follow a lot of its definition, and there won't really be any examples of how we work the math on these questions until 8.2. So, and I think, as always, when we start working actual math problems, sometimes the concepts become much clearer, because most of Chapter 8 deals with concepts and definitions and theories, but not examples. So for me personally, I've always found that, you know, I do the reading when I was a student way back when, and I may not have got everything, but I'd get a general idea. But once we started doing questions and coming up with answers and checking answers, I could go back and see how the formulas worked, and I got a much better idea of what we're really trying to do. So the first thing that they tell us over on page 414, down toward the bottom of the page, is that we're talking about a statistical hypothesis, and they say it's a conjecture, maybe more than an educated guess, about a population parameter. And there's doubt in the in our conjecture. It may or may not be true, but one thing that we're going to use to base our probability of saying a conjecture is true or not true is we'll go back and use our bell curve and our z-tables. So what you're going to see in 8.1 is very close in idea to Chapter 7 and confidence intervals. In fact, for the first few sections, we're going to come back and use this formula here. You may remember this is our how we calculate the z-value when we're dealing with confidence means, and how we had a correction on the standard deviation. So, and this was that central limit theorem. So it comes back into play also. Unfortunately, we don't start using this formula until 8.2. They're using 8.1 to sort of lay out some ground rules and give us some definitions. So the first definition they tell us, or they tell us that there are two types of these hypotheses, these conjectures or guesses based more than on a hunch, but on the standard normal or the normal distribution tables. And they tell us we have something called the null hypotheses, null being the German word for none or zero. And then we have also something called the alternative hypotheses. And the null hypotheses is written H sub 0, and the alternative hypothesis is written H sub 1. Some books use H sub A for that. But I'm going to tell you, I'm going to just give you an idea here. And by the way, they normally, for our null hypotheses, it says that there's no, and I have to go back a little bit because remember a lot of this is based on previous information. The idea of the idea of our statistics class is we take samples from a population, like a sample mean, and we try to generalize for the parameter. And when we're talking about samples, we're talking about statistics, by the way. And we generalize that toward, in this case, if it was a sample mean, we try to make generalizations about the population mean. As we've seen before, it's very unlikely that we can get an entire population that may share a common trait together. So we take a pretty good sample and then we base our conclusions off that sample. Okay, and of course we know that the larger the sample that we take, the more assured we are of getting a better answer, assuming that all the proper sampling methods were followed. So I'll just give you just right off the top of my head, although I cooked it up earlier, I will give you a situation. Let's say that we're talking about the average income of non-tenured professors across the nation. And let's say that our null hypotheses, let's say that we found out, or somebody in a report said, you know, the average income of professors or non-tenured professors across the U.S. is $40,000. Well, the alternative hypotheses to that would be that it's not $40,000. In other words, it could turn out to be more or less, and that would be the way that we write our hypotheses. We have the first hypothesis, the null hypothesis, says there's no difference between the parameter, or reading it down there, no difference between a parameter and a specific value, or that there is no difference between two parameters. And the alternative hypothesis is a statistical hypothesis that states the existence of a difference between a parameter and a specific value. Now, it may turn out that a researcher went out and did a really effective survey and came up with the fact that, found out that they had a sample mean of like $42,000. Well, that may or may not be enough to reject the null hypothesis, the one that says there's no difference, and then say, well, now we should change that to $42,000. Okay, the way that we make that decision is we will use the bell curve, and that comes later in this section. But at least now we're getting ready to talk about the hypotheses, and we have a little bit of an example. Let me just do one other thing real quick here, because we're coming up to an example that shows it. Let's say that the same, let's have the same idea, but a little different slant on it now. Let's say that a researcher, let's say that the established mean was $40,000 for that non-tenured professor, and let's say a researcher conjectures or suggests or hypothesizes that the mean is actually greater than $40,000. Okay, now that would be a different type of question. Okay, and finally we could have a situation where we go back to having the established mean of $40,000 for our null hypotheses. In other words, and that suggests that there is no difference between a statistic that we may get and the population mean. But another researcher may conjecture that it's less than $40,000. So we always have three situations. We have a situation, the null hypothesis always says there's no change, and I can't seem to get my pen to circle that. Null hypothesis always goes with the equal sign, or that there is no change. Oops, I should have written H1 here. But our alternative hypotheses can use a not equal, or a less than, or a greater than. And we still haven't done any examples yet, but at least we're getting closer to the idea. And that brings me to the fact that I want to look at all three of the situations on page 415. Now, you could simply read over these and probably get something out of it, but I want to relate it to the idea of the null hypotheses and the alternative hypotheses. And the first situation talks about a researcher wants to find out whether new medications will have any undesirable side effects, and is particularly concerned with the pulse rate of the patients that will be taking the medicine. Will it rise, or will it increase, or will it decrease, or remain unchanged after a patient takes it? And right now, the established pulse rate, population mean, this is on the top of page 415, is 82. Now, notice that the researcher doesn't know, they're trying to find out side effects, and this is true whenever we have an equal sign in our null hypotheses, and we don't know on which side of the mean that the results are going to fall. In this case, the alternative hypotheses would be it's not equal to 82. So the established pulse population mean is 82. They're going to apply this medicine to people that in some type of study group, and they're going to monitor what happens. Maybe some pulse rates will go above, or they don't know whether the pulse rate will go above or below or stay the same. But this is a hypothesis, or this is a test we would set up. And to just jump ahead a little bit, this is called a two-tailed test, where we would expect to find our sample means in this area here, and then we will have z-values, a positive and a negative z-value, and would then put this test we're not talking about the study yet, but I just want to jump out a little bit ahead of time. Any value that we got by finding a z-value that fell within this area here, and now this area is called the non-critical region, and then the tails are called the critical region. Now, if we got a z-value that fell within the non-critical region, we would just stay with our null hypotheses. There's no change or in the established pulse rate. However, if we had a good sample and we got a number that was larger than what we call our critical values here, then we would consider rejecting the null hypotheses and adapting the alternative hypotheses. Now, we're not working any questions like this yet, but we will be soon, and all of this will become much more clearer if it's not getting there already. How about situation B? A chemist invents an additive to increase the life of automobile battery, and the lifetime of automobile batteries without the additive is now 36 months, and then we want to know what the hypotheses would be. This is situation B. Well, the null hypotheses would be that there's no change in that battery life. In other words, that the mean battery life is going to remain 36. And if you notice the difference in the idea of the words here, the idea is to increase the battery life. Okay, so the when increase or go up or more, all those words, and they give us a lot of those buzzwords on table 8.1 on the next page. But our alternative hypotheses for this one would be that the mean would actually be more than 36, and that increase would be due to the fact that they're using this additive. And this is called the right tail test. Here would be our mean, We're going to, of course, turn this into standard deviations. And we would have, since the idea of increasing, that puts us on the right side of the mean, this would be our critical area for a given z-value. And everything to the left of that would be non-critical. Now they're going to give us these definitions in a minute here, and remember that the z-value there is called our critical value. And we know how to find these from previous experience. So we're going to have a non-critical region and a critical region. And we're going to use this formula here, because we'll have all kinds of information. And if this formula gives us a value, a z-value that is bigger than our critical value, we're going to reject the null hypotheses. Okay? And we'll say, because we're so far out in that tail there, that we have not chosen a sample mean due to random error, we've really made we're deep into the critical region beyond our critical value, and that's how we decide whether to reject the null hypotheses or say something to the effect that, well, you know, I didn't get a number, a z-value big enough, so it is not enough information to reject the null hypotheses. So anyways, so far we've seen that there is something called a two-tailed test. That's this situation. All right, CR for critical, excuse me, well, for the two-tailed test, this is non-critical. And then these two regions here are critical. And of course, there's going to be set off by positive and negative z-values. So we got a non-critical region and then the two critical regions, and that's for a two-tailed test. And we just saw for a right-tailed test, we have this situation, just sketched. Lost my pen there. I don't know why my pen doesn't like to shade very well, but this would be our critical region. This would be our non-critical region in terms of a calculated z-value. And even if we don't get every little nuance of this now, believe me, as soon as we get into 8.2, we will see everything. Okay, so then the last situation we would have would be called a left-tailed test. And that turns out to be situation C on page 415. Okay, and this time we've got a contractor and he wants to lower heating bills by using a special type of insulation. And right now we know that the average bill is $78, and we would like to see if the treatment or the change using this insulation is going to make it less money. Okay, so it's what's called a left-tailed test. The fact that there would be the hypotheses that would represent no change in the bill would be that the bill will remain $78. Okay, obviously we like to pay less, and so the alternative hypotheses would be the bill will fall below $78. Now, the contractor may go out and take a sample of 100 people and calculate the bill is now $76 with the insulation. That may or may not be enough information or good enough information to reject the null hypotheses. Okay, because on a left or on any of these tests, don't forget we have to identify a z-value, and we have to use this formula here. From chapter 6, and if we might get a sample mean that falls below $78, but does it fall enough below $78? In other words, in terms of a calculated z-value that would make us consider rejecting the null hypotheses. That's what they're not telling us yet, but we will get to toward the end of this section, and it's certainly all through section 8.2. Anyway, you can summarize the toward the bottom of page 415. They give us a little table there how to write the null and alternate hypotheses for a two-tailed test, a right-tailed test, and a left-tailed test. Okay, and by the way, just to finish off on this example, the critical region would be in the left tail, and all the remaining area would be non-critical. Okay, so study that, or be aware of that on the bottom of 415, and then on the top of 414, no, that was 415, then on the top of page 416, they have a table of just common English phrases that lead them to, for example, the things that we think about a right-tailed test would be like greater than, above, higher than, longer than, bigger than, increased by. Those would all be greater, or English words that suggest greater, as opposed to left tail, which less than, below, lower than, shorter than, smaller than, decreased or reduced. Okay, so by looking at that table, I think you can follow example 8.1 and get an idea about how they came up with the null hypotheses, the one that says there's no change, and the one that says there is change. That would be the alternative hypotheses. Okay, and again, I just don't feel comfortable reading what the book has to say about this. I feel more comfortable explaining the high points and leaving the reading to you, especially since we'll be going over and over this material in 8.2. But we finally get down to their idea on the next page, which is 417, about a statistical test. And it says it uses data obtained from a sample to make a decision about whether the null hypotheses should be rejected. Okay, so recall, in our first cases, we're going to be using this, which we should really be familiar with. Let's say, for example, that we were doing a right-tailed test, and we would have a critical value and a critical region, and there'd be some z-value here. U equals k is just a simple way to say that the parameter, some type, in this case, it'd be some value, and our alternative hypotheses would be u greater than k. So, let's say that we put this formula, we would obviously have a study, we would have a sample mean, we would have a population mean, we would have a standard deviation, and we would know our sample size. If our z turned out to be greater than the critical value that separates the non-critical from the critical, then we would reject the null hypotheses. If we get a z that would be anywhere in the other or non-critical region, then we don't reject the null hypotheses. But the way the book has lined this up is they're not giving us this information until we get to 8.2. But we'll be using the equations for z quite a bit. Anyway, they tell us that the numerical value obtained from a statistical test is called the test value or the test statistic. So that's what they're talking about on the examples I just gave there. Okay, there's some more theory reading here, and they have a little data table on the top of 418, and they have a really good reminder. Before I talk about the errors that we can make, they use a everyday situation when we're talking about like a jury trial, and this is at the bottom of 418. Okay, and they're using the idea of like a court trial. We can say two things. The defendant is innocent, or the defendant is not innocent. In other words, they're guilty. Okay, so that's one way we can think about the what we're proving here. We say somebody is either guilty or not guilty, but when you say that they're not guilty, that still leaves, in other words, they were proved by the evidence submitted that they were not guilty. But we don't use the term unless somebody obviously confesses to the crime that somebody's on trial for. We use the terms guilty and not guilty, but we don't use the terms innocent. And what I'm trying to say here is that there will always be doubt in our answers, even though they're based on probability distribution or our z-tables. Remember, we can be like 90% confident or 95% confident or even 99% confident, but there is still an element of doubt or probability. Okay, so that's a lot of what the material is trying to tell us on 418. And there's one thing that we can mention, although I don't think we'll be seeing much of this again, but there are, when we put these different data tables together, there are two different types of error. And it's nice to be familiar with them, but we won't be doing much with them, if anything at all, as the chapter continues. There's a type 1 error, and that occurs if you reject the null hypotheses when it's really true. And then a type 2 error would happen if you don't reject the null hypotheses and it's false. Okay, so that kind of ties in where like the at the bottom of the page of 418 and on the top of 419. Okay, and then finally the last thing before we can go look at a few examples and finish off with some of this theory here would be the level of significance is the maximum probability of committing a type 1 error. This probability is symbolized by the Greek letter alpha. Okay, in other words, we have seen this alpha before. Alpha, just to give you an example, if we were dealing with alpha equals 0.05 and we were talking about a two-tailed test, well, we go 1 minus 0.05 and get 0.95, which is like the 95th confidence interval. And we know, so that we would know that 95% of the graph or the sample means would lie within this area. And then the other alpha over 2, recall, would be cut into the tails. Now, this is Chapter 7 stuff. We're going to do things differently in Chapter 8, but I wanted to make sure that we know that we had seen alpha before. And now they're telling us for a test, a type 1 error, which again is just passing information, that the probability of making this type 1 error is called alpha, and I think I've done an explanation of it here. If we are using alpha 0.05 for our critical value, or excuse me, our area, then there is that 5% chance that we've made a type 1 error, which is if we reject the null hypotheses when it's really true. Okay. Anyway, we finally get to some examples at the bottom of page 420, and you will find that I've already mentioned the first things in passing here, but I'll show them again, and this is on the top of 420. We're going to talk about the critical or rejection region. I'm just going to, this is different than when we were dealing with sample means, because we were interested in sample means falling in within a given alpha over 2. And then, of course, this would be our non-critical region. Okay, so I'm going to follow along with their definitions here. The critical or rejection region is the range of test values that indicate that there is a significant difference and that the null hypothesis should be rejected. So we've got critical, I'm just using a two-tailed test for example here. Remember that each of these critical regions, if we were using a two-tailed test, would be set off by z-values. And if our z-value is larger, let's say that we're using, you may recall for the 95th confidence interval, the z-values were 1.96, negative 1.96, and positive 1.96. Let's say that we put this calculation, can't help but getting a little bit ahead of myself here, but let's say that we have a situation, a two-tailed test, and recall that that would be where the null hypothesis would be that the mean is equal to some value, and the alternative hypothesis would be that it's not equal to that value and could fall on either side of our mean. This would be 0 as a standard deviation. Okay, if we got a z, in this case it was bigger than 1.96, we would reject our null hypotheses and go with our alternative hypotheses. If we got a z that was not bigger than, I'll say it differently, if we got a z that was less than negative 1.96, that would put us into this critical region, and then we would reject the null hypotheses. If we got a z that fell anywhere in between, those values, in other words, this would be our non-critical region. And we would not reject the null hypotheses. So if we got a z-value that fell within the hump there of the bell and not on either side of the positive or negative 1.96, then we would not reject. Okay, so, and again, they tell us that the values, and I've used here, these are called critical values. Okay, so far we've seen that we have a critical region or regions, depending upon if it's a one or two-tailed test, and we have a non-critical region, and we have critical values. And again, as soon as we do our first example in 8.2, all of this comes into play. Then they tell us that there's a little story there, or a little blurb below, about halfway down. A one-tailed test indicates that the null hypotheses should be rejected when the test value is in the critical region on one side of the mean. So let's quickly, we just did a two-tailed situation. Let's do a right-tailed test. Let's say our critical value, make it 2.33 this time. All right, CRIT for critical and non-critical. Let's say that we put our z-test on this. Here's the formula. And let's say our z-value turns out to be 2.65. Well, 2.65 is bigger than 2.33, so our value is bigger than the cutoff or critical value there, so we would reject the null hypotheses. Now, what if we had a left-tailed test instead of a right-tailed test? We'd use the exact same situation. Let's say that we did our z-value again and came up with z equal to 2.01. Well, 2.01 is not less than negative 2.01. Negative 2.01 is not less than negative 2.33, so we would not reject the null hypotheses. But what if our z-value turned out to be negative 2.46? Well, negative 2.46 would clearly be to the left or further into that left tail, and if that was the case, then we would reject the null. Okay, I'm kind of free associating here and using a lot of examples, but I know for a fact this will help when we get to 8.2, and it keeps me from just doing a dry reading of what the book is trying to say without explaining it. Okay, so let's, now I'm going to just mention something right now, and whenever we're talking about these critical values, remember that we have, I'll put it in the way that the book does, and I'm going to jump up to page 422 real quick. When we're talking about critical values, remember that we have these three confidence intervals. Okay, and each of these, of course, is associated with the two alphas, and maybe alpha over 2, depending upon the situation, whether it's a two-tailed or one-tailed, etc. But if you notice on page 422, all the values for two tails or right or left tail for these critical values that we use all the time are summarized there. Now, you might have a homework question or something that, as an exercise, asks you to find a value that isn't one of our common values, but I can tell you on the quiz and on the test that we will be using these most common values, okay? And all their critical values, or those, I should say, alphas, and all those are summarized on page 422. Recall also that our last test is open book, so you can just flip back and refer to these. You don't have to write up a note card or anything like that. Anyway, what I wanted to do before I went to figure 8.4, I just lost my page here. Okay, it's nice to know, and we've done this before, they want us to find the critical value. We have a test, and we want to have its level of significance, or our alpha is 0.01, and it turns out this is a right-tailed test. And that means that we have a null hypothesis that is equal to some parameter, and our alternative hypotheses would be that it's greater than the parameter. Okay? And if it's, recall that alpha 0.01 is the same as 1 minus 0.01, or 0.99, or the same as saying the 99th percent in terms of confidence. Anyway, I'll put a fresh page on this. Here's the situation. One-tailed test, 99th confidence interval. 0.99 of the graph is in the non-critical region, and 0.01 is in the critical region, which I'm going to try to shade. Now, there must be a cutoff value, or what we call a critical value, z-value in this case, that separates the non-critical from the critical. And to find that, you may recall, we have to go into our z-tables, and we have to read across and down until we find the closest value to 0.99. Remember, that's the way the z-values work. So 0.99 of the area is to the left, and we can read that directly from our z-table. And it turns out when we come down and over, the closest value is 0.9901, and that represents a z of 2.3, and then on the other side we have 0.03. So our critical value would be 2.33. If we worked a z-value using this formula, if we got a z-value bigger than 2.33, that would put us in the critical region. We would reject the null hypotheses. Let's say we got a value like 1.99. That is not in the critical region. It's in the non-critical region. We would not reject the null hypotheses. Okay, well, they've done, that's pretty much, they also used the same setup there for the left tail at alpha 0.01. It would just be this situation, where this is the critical, this is on the top of the next page, the non-critical. And you may recall that there is symmetry with our graph, okay, our standard normal distribution. And if when we did the right tail test for alpha 0.01, we got 2.33 as a critical value, then it should make sense that when we do the left tail test, there's a couple of ways to find it, but since there's symmetry with the graph, if this represents 0.01, then when we're dealing with the left tail, the 0.01 would just be on the other side, and it would still be 2.33, except now it's negative. And this is what they're trying to show us on the top of page 421. Okay, well, we've got, I'll let you read over because we've done so much already with the two-tailed test, and that's the example they give on page 421 at the bottom there, and they go all the way to the top of page 422, and then, as I mentioned, they list every critical value for our three most common probability levels, or confidence interval level, the 90%, the 95%, and the 99%. Okay, well, finally, we're going to work just a couple more questions. Since we've done this before, I may not work all of them, but I'll try to refer to them. But this is something we did back in Chapter 6, I think, and then again in Chapter 7. This is example 8.2. So let's see the first one here, and this is just for practice. We're supposed to find a left-tailed test with an alpha of 0.10. That looks like this. Remember, it's left-tailed, and immediately the hypotheses would be that our sample mean, our population mean equals some value, and our alternative hypotheses would be it's less than that value. Okay, and we know that the non-critical region would be the 90% to the right of that critical region, and we know that our alpha is 0.10. Now, there's two ways to do this. You can find out what the right tail for 0.10 is. You'd have to do that by using 0.90 and then finding the area to the right. Or because the way our tables are set up, it says we can just go to the back to our table and read it directly. And it turns out the closest value is 0.1003 as a decimal, 0.1003. And remember, we were dealing with 0.10, so we'll saw off that 3/10,000ths, and the closest value that's associated then with that critical region of 0.10 would be minus 1.28. And by the way, if we had that same problem, except we wanted to find out if it was a right-tailed test, its value would be 1.28, okay, because there's symmetry with our graph. And the critical value for the region on the left, representing 10% of the graph, would be the same critical value on the right. The only thing that's different would be one of them would have a negative value and the other one would have a positive value. Depends on which side of the mean that we're on. Okay, well, I'll leave it to you to look at letter B and letter C. But again, I want to emphasize that all the values that you're going to need for the majority of your homework and on the quiz and on the test can be found summarized on 422. So it would really be helpful for you, don't figure these Z tables out, in other words, going from an area to a Z, just go back to this table here. If you're a little rusty on how it's done, well then hopefully these few homework examples or few book examples I've given are helpful. Okay, well, they've got one final thing here, and again, as soon as we get into the next section, I'll be working several examples and I'll relate each example back to what we've done here. But at the bottom of 424, they tell us what we're going to do when we finally, in section 8.2, set up our own experiment or make our own hypotheses and come to our own conclusions. We need to state the hypotheses and identify a claim. Claim is not quite as important to me as the hypotheses. Find the critical values. We just saw we can get those critical values in almost all cases on page 422 or from our Z tables in Appendix A. Compute the test value. What they mean by that is use this formula. Okay? Make the decision whether or not to reject the null hypotheses. And let's just, again, say we're dealing with a two-tailed test. Let's say that it was at the alpha equals 0.01. And so that would put 0.05 in each area for alpha over 2. Okay, and even if you don't recall all this stuff, it's okay because I'm just using it as an example to close this off. Okay, if we got a Z value greater than 2.58, we would be further into the critical region there, or beyond the critical value, we would reject. If we got a Z value less than negative 2.58, remember in a two-tailed test, we don't know on which side of the mean we could possibly fall in. If we get a value that's less than negative 2.58, we would reject. And because both of those are in critical regions. And then finally, if we got a z-value that was greater than negative 2.58 or less than positive 2.58, those would be in the non-critical region, and we would not reject the null hypotheses. Okay, well, one thing I like about this book is on the homework for the section that we've just completed here, they're going to ask you a number of questions that deal with the theory and finding some critical values and some definitions. I guarantee you, if you understand the majority of the homework questions and understood the bare bones stuff I've thrown out about hypothesis testing and critical values and critical and non-critical regions, that 8.2, which is the heart of this chapter, will make a lot of sense, or make more sense, because we now have something to build on. So I'll be back with 8.2, which is called a z-test for the mean, shortly. And I will make sure every time we do one of their examples or discuss answer that we relate it all back to 8.1. Thank you.